Thank you for the introduction and welcome to this presentation. I'm really excited of being here, sharing with you what I've done during my PhD about on-chip communication and threat that we found on modern platforms. So first of all, who am I? Well, I'm an academic. I work at the University of California, San Diego, and I did my PhD in Italy at the Retis Lab Pisa in an embedded real-time system lab. I've been working mainly in the previous 4 years on hardware security, and we focused a lot on access control systems for hardware in the previous 2 years. But my thesis was mainly on timing predictability, safety, and security mechanism for FPGA SoC platforms. We've also done some work on timing predictable DNN acceleration on FPGAs that at the end there are references if you are interested. Okay, this talk, basically, what I'm trying to introduce you, it's how we explore, analyze, and address security and safety concerns that we found in a popular communication standard implemented in heterogeneous platforms. And we detected a couple of threats that are able actually to create dependencies among multiple models. That is something that is very critical in safety systems, and deals to unbounded bandwidth distribution and denial of service of resources such memories, shared memories. Also, the lesson I learned and the solution we propose and some guidelines at the end of this talk. Okay, just to get all of us on the same page, basically we work on safety critical systems, and these systems are systems that they can never fail, actually. So because a failure of this system would create a threat to life or even worse condition. So avionics, space applications, or autonomous cars, also like regular cars, are examples of this system we take care of mainly. And the requirements of these systems modernly, currently, are really strictly, because this system requires many times to accelerate deep neural networks for their requirements on image detection, for instance. So they need high throughput, but also high power efficiency because they are embedded. Plus security requirements, of course. I'm not going to go through that. You are more expert than I am in that. But also very important is safety. So timing predictability. So you want that a critical task execute within a deadline, and isolation among multiple models that execute on the same system. Among the heterogeneous platforms that are available, there are GPU SoCs and FPGA SoCs and custom SoCs that are very common right now for implementing these kinds of new generation safety critical and security critical systems. GPU SoCs are great. They are the common choice, let's say, but for some application, unfortunately, they cannot be applied, like for avionics in particular, or also some other critical applications. So we focus a lot on FPGA SoCs and on GPUs to provide hard constraints on what we would like to propose, hard timing constraints. If you look inside an heterogeneous platform, what you're going to find, basically, is a set of controllers and a set of peripherals. The controllers are the active guys on the bus, basically, that send requests to the peripherals. And these are processor, DMAs, hardware accelerators, etc. The peripherals are just in charge of responding to this kind of request, providing data or accepting the data in case of a write. They are interconnected with an interconnect. In this case, this is an AXI interconnect, which is the de facto standard for communication in most of the platforms that we have seen. The peripherals are shared among the controllers. Typically, think of a shared DRAM memory. And the interconnect is in charge also of arbitrating the access of the controllers to a single peripheral or to a multi-peripherals. Multiple controllers, however, can generate heterogeneous interference, and we've seen that the protocol itself leaves a lot of freedom on how the requests for transactions are issued on the bus. And this can create some issues that I'm going to introduce you later. So the standard itself I've already introduced you. So it's a standard from ARM, and it's a great standard, very popular because it allows great flexibility. And in this case, each controller edge and each peripheral has separated access to the system interconnect. And it is something that we really like because it provides isolation, electrical isolation among the controllers. And this is something that interests us because it allows any controller to communicate directly without interference from the other, with the system interconnect at least. However, we found that there are dependencies inside that I'm going to show you later. The definition of AXI defines basically a manager and peripheral interface with 5 different channels that are handled independently. And this is the representation. Okay, this is the platform, our target platform basically, that is a Zenc UltraScale Plus from Xilinx. We also target the Zinc 7000 platform. All of the work presented here is applicable to both of them. And basically this kind of platform is, it can be seen, it can be simplified as in that simplified representation as composed of a processing system that is this purple one here that includes multiple processors like Cortex A53 and the real-time processors. And a programmable logic where you place a custom hardware accelerators or custom processor, whatever you want to implement inside of the custom logic. So we're going to use the programmable logic, to deploy controller managers and to analyze what happens in the bus interaction whenever they interfere among each other. Our threat model assumed that the controllers are untrusted, and we assume that are untrusted because they can be actually get from third-party IPs. It's very common actually, but they can also be affected by bugs because of superficial verification, or they can be malicious also. We trust the interconnect and the peripheral. We don't get inside the looking for the bugs inside of that kind of modules. And we focus on the availability of the controllers to the peripherals. So we would like that in any time the controllers can access the peripherals they're entitled to, of course. So how we started our journey? Well, FPGA SoCs were becoming very interesting for the implementation on next generation system, embedded systems, because of the reason I was telling you before. And the challenge we wanted to face is timing predictability on the bus and memory interactions. And at that time, there was nothing, like there was no academic work on that. So our main aim was to bound the response time of the bus and memory interactions. However, we ended up at first facing some security and safety issues that we had to solve, and after that we proposed some work, a couple of work on timing predictability. So the test architecture I'm going to start with is this one here. This is a generic one, but in general we got here 3 hardware accelerators that we use DMAs from Xilinx, so commercial accelerators. We use the stock interconnect also from the vendor, and we create this architecture. What we wanted to do at first is test how the assigned bandwidth of the hardware accelerator can vary according to how you configure the modules itself, so to see whether there were dependencies on that. So what was implemented here, what is implemented here, we checked the datasheet, it's a round-robin arbitration. So what we expected from a round-robin arbitration is that the bandwidth that is given to each of the model is fair. So we did this architecture. We take one of the guys under analysis, the guy under analysis, the one in red here, and the other 2, we make them generating the most of the traffic they could, so accessing the bus in the most greedy way that they could. And we wanted to measure what is the bandwidth associated to this guy. So, and the bandwidth is this one. So what we saw is that here there is configuration of the interfering hardware accelerator. I'll show you later what do I mean with that. That the bandwidth of this guy under analysis associated with him goes down from the 33%, which is the one expected, the fair bandwidth distribution, to something like 3%, something like this. So instead of being a property defined by the interconnect itself, the configuration of the interfering modules was able to endanger the access to the bandwidth of the hardware module under analysis and decrease the access to the bandwidth of more than 10%, than 10 times, sorry. So we did investigation on that. We did it on both of the platform, the Zinc 7000 and the UltraScale Plus. Here I've got a short demo. We put integrated logic analyzer probe, and we would like to plot what happens actually on the bus, so why this happens. I've got a short demo on that. So let me stop here. I went to the end. Okay. So this is the architecture for the FPGA. And we got 3 DMAs that generate traffic, and this can be whatever kind of controller you would like to simulate. The system interconnect is just a standard system interconnect that is connected to the processing system to access the memory, in our case, so the shared memory. There is other logic for configuration, we don't go into that. And this is the integrated logic analyzer that we do to probe all of the that we use to probe all of the interfaces, the AXI interfaces, and see what's going on. So here I've already synthesized the design. What I'm doing is writing this design inside of the board. So in the programmable logic, I'm uploading it to the programmable logic. And after that, I launch the SDK from Xilinx. And here there is some code that we use to set up all of the modules inside of the system, the DMAs. And yeah, we connect the UART, the terminal, to get like some result from that. After initialization, we can see the track coming from the system integrated logic analyzer. So it is uploading. We set up the trigger to get a specific moment in time. Okay. And now with the software, we configure the traffic generators in the FPGA and we make them executing. Should be fast. Okay, here we go. We got the track. So this is the track, the actual track collected on the FPGA. And what you see here, there are 4 interfaces, AXI interfaces. These first 3 are the interfaces that are connected directly to the hardware module. While this guy here, this interface here, is the interface that comes from the processing system. So it provides you data and accepts the data from the FPGA. So this one and this one are the 2 interfering hardware module, while this one is the module under analysis. This yellow one are the data that comes from the memory, and this blue one are the write data provided to the memory. Okay, so they're all accessing the bus in the most greedy way that they can. However, you see that how the data that comes from the 2 interfering, the 2 interfering get most of the data, while the guy under analysis, the hardware module under analysis, just get a small chunk of data. So like here, they are like maybe 12 words of data, while here you have 250 or something. So most of the data are going to the interfering one. Sorry about that. Okay. Should be good. Yeah. Okay, so we analyzed the issue and to try to understand what was going on. And basically what we did, what we saw is that actually the interconnect was serving the hardware module following an actual round-robin schema as expected from the datasheet. But the granularity on data, it actually depends on how the module requests the data. So the module can submit a request and request more data with respect to the others. And in this case, you serve the transaction with round robin, but when the data come back and you have the equivalent round robin for the data, there are more data going to some other modules with respect to the other. And this causes an unexpected bandwidth loss with respect to the guy under analysis. So we did a very simple mathematical analysis on that to understand how was the entity of the issue. And considering one single module that has the burst length, which is the configuration we actually check, to 16 words, which means you ask for a single transaction, you got 16 words of data for each single transaction, and you got one single. This is a table where you got the number of interfering hardware accelerators and the burst length of the interfering hardware accelerators. So very briefly, what we see is that just with one single interfering module that can do transaction longer with respect to what we can do as guy under analysis, I will show you later why. The drop is the 88%. So you pass from a 50% of bandwidth assigned to something like 6% or something like this. Okay, so you're guessing now if this is a real issue. Should we care about that? How likely is that to happen? Well, consider that controllers can come from different sources. And You can develop all of your controllers inside of your system if you want, but it's expensive. So if you want to develop a processor, for instance, and integrate it inside of your system, you may need time. So what is very popular is getting controllers from third party, right? You get them from outside. So you can verify them sometimes, yes, sometimes you can't. So it depends. Also, there are different development methods for these controllers. They can be developed using standard RTL, or also high-level synthesis. That is something that FPGA's vendors are pushing a lot right now, because it allows people that doesn't have like a strong background in hardware to develop accelerators, but also other hardware construction language, of course. So this can create challenges. First of all, for verification, because the model can be very complex, and if you are able to get the code of the model, you have to verify that. Most of the verification, many times, is done through manual inspection, so it's error-prone, right? If you have HLS-generated code, so from high-level synthesis compiler, you go to an RTL, that code can be very, very difficult to analyze, because it's not done to be read by humans, actually. But also you can have third-party models that are encrypted, and you can actually verify them. So it creates dependencies, and also consider that these models, many times are software configurable. So if you leave also this degree of freedom of configuring through software, it can create other issues. There are different versions of the standard also that they can be combined together. And in the case before, we got an AXI 3 and an AXI 4 combined, and the AXI 3 guy was able to issue transaction for 16 words at most, because the standard was that. And AXI 4 was able to ask for 256 word transaction, so it was actually impacting the bandwidth of that. And also, with HLS, they're pushing a lot on HLS, but these abstract a lot what you are doing with your hardware. So these are low-level details that if you develop, if you know about that, you can set up some pragmas on that, of course, but they can be hidden from some people that they want just to develop some hardware model. So what I learned from here, summarizing, is that leaving the controller defining the structure of the transaction can create a problem in the bandwidth distribution. And it can affect the availability of the shared resources, in particular on the memory. That's what we were focusing more, actually. We have a proposed solution and experimental results later in this presentation. I will go now into another problem we've seen that, to me, is even more interesting than this one that I showed. So, after using DMAs from Xilinx, we started developing our own AXI-compliant models, because we needed a model that we could be able to monitor from the cycle. So we've been able to generate traffic at the cycle accurate level. And we found a very interesting behavior here. This is the architecture scenes that we're going to see. And still, we are operating on both of these platforms. Okay, let me stop here to present the architecture. 3 hardware models. These are the models that I develop. These are custom, fully compliant AXI models. We got an interconnect plus some other logic here that don't consider that is a solution that I'm going to propose you later. Some configuration logic here, and system interconnect and a system ELA. And we're accessing here the memory. Okay, we're doing the same thing. I can skip some parts eventually. So we are actually writing the bit stream. We have some code running. Okay. So we configure one of the 3 modules to inject a specific behavior that is compliant with the standard, but it creates a problem. And right now I'm going to show you when we're going to collecting the waveform. Okay, setup is running. Here we go. Let's zoom the track a bit. Okay, here we go. Sorry, I'm not very good with this Keynote video integration. Okay, let me stop there. Okay, so 3 hardware modules here. FPGA APS interface data, where they accept the data. In this case, we are issuing write transactions. So the first guy here, the top one, is issuing for request for transaction for write for some length. Is not important. And the other 2 models in the system are doing the same. So the requests are eventually granted at the FPGA APS interface to reach the memory, and here are the requests. These two guys here, this guy here and this guy here, are already ready to give the data, the write data. These are the write data provided to the system interconnect by these two hardware modules. But this guy here didn't start providing the data yet. So what is the problem? Is that the round-robin arbiter here submitted as first request the request of this guy here. So this is the first in line. And as long as this guy here does not provide all of the word of data on another channel, by the way, it's another channel that is handled independently, the bus, the write bus to the memory is stuck. And the other two guys, even if they are already provided all of the data, they cannot access it anymore. We analyze that. So this is the same waveform track, but it's a simplified one just with one transaction and two hardware modules. Here's the summary of what's going on. But basically what happens, and what it comes from the standard, is that as long as one hardware module book the bus submitting a transaction, the other guys in the system, they cannot provide any word of data to the memory as long as it does not complete the whole transaction. So this is from the protocol itself, and it says that the interconnect that combines write transaction from different managers, so our case, must ensure that it forwards the write data in the address order, in the same address order. These are different channels, by the way. They are independent, but they create an dependency here. This is something that in AXI 3 was kind of solvable, maybe in a bad way, but it was kind of solvable. But in AXI 4, the interlevel of transaction has been deprecated, and it generates this problem. So we analyze it, and basically, what we saw is that the bottom line is that the interconnect itself is trusting one hardware module, like this guy here, that after submitting his request for transaction, is gonna provide all of the data for the transaction, and is gonna provide them rapidly, and is gonna complete the transaction as soon as possible, and leave the bus to the other guys in the system, of course. However, in this way, a single module can deny the access to the other guys in the system, but what is more interesting is that the protocol itself is not broken. So there is nothing in the protocol that says that you should provide the write data immediately after you submitted the request. So the consequences is that this is just a summary. As long as a transaction is kept pending by another module, the other guys in the system cannot access the shared bus, cannot access all of the peripherals, not just one peripheral, all of them. So the availability of shared resources is compromised, but also the network is left in an inconsistent state. So you may require a system reset in here to restore a safe condition. And it's something that in safety critical system we don't want. Okay, we already say that. Again, should we care about this? So first of all, what are the potential sources of this problem, of bus stall problem? You can have malicious behavior, you can exploit this. I'm going to show you later also that I've got some ideas that, there are some behavior that are kind of borderline that you could exploit this behavior. It can be also, most probably, a misbehavior or a faulty model because bugs in the system are very frequent and they're very difficult to verify, but also caused by optimizations and in particular speculative bus access that I'm going to introduce you later. So how you exploit this? Well, basically, it's pretty simple from the hardware point of view. You just have to act on this signal that is the W-valid signal that it says whenever there is a data word available to the common bus, basically. And you can directly acting on that line, on the W channel, eventually, if you're able, for instance, to write something on the FPGA. Or you can also delay the write data production inside of a module if you want, and you can be creative on that after having issued the request. But there are also some interesting behavior we've seen that create dependencies with read operations, for instance, in DMAs. So when you have to move data from one source buffer to a destination buffer, I'm going to show you later 2 examples. Actually now. So here I would like to show you how this phenomenon is common. And we take this first hardware module that is the Xilinx Deep Learning Processing Unit, DPU, that is the most recent DNN hardware accelerator proposed by Xilinx. It's something that we really like and we like to play with. So it's part of the Xilinx VTCI framework, and this is the actual design of the guy. we get actually the stock hardware from the VTCI, and we customize it to add some profilers and to add some integrated logic analyzer to see what this guy was doing. And this is a track from an actual execution of the model executing a plate number detection, if I remember correctly, as the network. So basically what you see here is that the model is asking for a write request. It delays, this is for 108 words of data. So it means that I want to provide 108 words of data. For 300 cycle, more than 300 cycle is not providing anything. This guy here already booked the bus if he's in a shared architecture as I showed you before. Then it provides 12 words of data, and then it's stall again. So at this point, this is like 540, in 600 cycle, it did not complete the transaction yet. It should have been completed in 108 words in the best case scenario, let's say, right? But in this case here, you block the access to the others, to the memory, to write to the memory. Another example is on the direct memory access that is from Xilinx, the CDMA. And here there is an interesting behavior that we have seen. We did the same design, actually, a similar design with probes. What we see here is that whenever you set up a source buffer and a destination buffer and you trigger the execution, the read and the write are issued at the same time, in the same clock cycle. What does it mean? It means that here you're booking the write bus even though you didn't receive the read data yet. So if you are able to affect the provisioning of the read data, if you're able to inject here an address that goes somewhere that is a peripheral that is misconfigured or something like this, you're affecting also the access to all the write bus from all the other guys in the system. Okay, I'm not going to stress that much on that. The impact it's on security, of course, because here we are able to endanger the availability of the peripherals. Also on safety, because we create circular dependencies again in modules, and we broke the isolation. That is something that we don't want. But it creates also problems on the average performance. We were not happy with that, so we did a realistic test on a mixed critical scenario that is inspired by some common functionalities that are required in a modern autonomous vehicle. So in this case, we split the computation on two different levels, high critical domain and low critical domain. In the high critical domain, we got a deep learning accelerator, in this case the ChIDNN still from Xilinx, and a critical sensor actuator. In the low critical domain, we just got a generic data mover that is just generating traffic and eventually injecting faults. So this is the ChIDNN hardware accelerator. We modified it. We take the standard hardware and we modify it to inject a critical accelerator and a malicious misbehaving model. So what we did is using the stock Petalinux image from Xilinx for the ChIDNN, and we put the FPGA our setup. We would like as requirements that the ChIDNN itself can execute with a minimum FPS, so in a safe way, let's say. While the critical model, we put some hard real-time constraints, so we put a deadline for them. And this is the execution whenever, the performance of the execution whenever the misbehavior guy does not introduce any fault in the system. However, whenever we trigger any movement from the guy that got a fault, we couldn't access anymore the bus itself from all of the system. And what we got is that the response times of the critical hardware model is unbounded, and the accelerator for DNN cannot compute any frame. Okay, that's just a summary. We already said that. So what I learned from that is that leaving the controllers the freedom of delaying their data provisioning can affect the availability of the resources, and it can be exploited actually, and we have seen how. We propose multiple solutions on that, and I'm going to be fast on that because we don't have time. So basically, the first problem is unfair bandwidth distribution. So here, the source of the issue is that the data structure of transaction is left to be decided by controllers, so you don't have any control on that. And this can even change dynamically during execution. So we need something to equalize the structure of the transaction that goes to the interconnect. Unfortunately, we cannot just take a constant for the burst length signal, but we need something more complex. So what we propose is the AXI burst equalizer, which is a very essential model that uses a concept that is very common, actually, splitting merging, actually. And this guy is put between the controller and the interconnect, and you can configure it with a nominal size. And we got also a response time analysis for real-time systems in that if you want to decide how to configure it. It makes transaction homogeneous, and it keep the transparency and the compliancy with the AXI standard from one side to the others. So, and it enforces a fair per manager granularity of data. That's the most important thing. So what is all of the transactions that reach the interconnect are homogeneous in this case. So there is no heterogeneity anymore in transactions. And so when you get back the data, also the round robin cycle on data is equivalent is fair also for the data besides the transaction. These are just experiments. I'm going fast on that. Basically what we've shown is that with our solution, we've been able to keep the bandwidth fair and predictable, and keep a safe access to the bus independently on how the hardware models behave on the bus. Preventing the denial of service on the bus. So in this case, the source of the issue is that controllers are trusted to complete, eventually rapidly, the transaction. So our solution should be able to recognize when a stall endangering the system. In our case, we call it system schedulability, real-time systems, and restore a safe condition of the bus. So re-guarantee the access to the other hardware accelerators, hardware modules in general. So how do we know when a stall is dangerous? Because we saw that many models introduce stall in the system, so we want to leave some flexibility. So we defined a model on that. I was in a real-time system lab, so we like models and worst-case analysis. So we defined a model for hardware models, interconnect, and peripherals, and we propose a worst-case analysis that is able to understand how much time you can stall the bus before you create a condition of threatening for the system that is correlated to the slack of the models. We have full mathematical analysis in the paper. I'm not going into details of that. Please ask me later if you are interested. And then, however, we need something to take back the control of the bus, because when you inject a fault, you can't actually access the bus. If you don't complete the transaction, you cannot abort the transaction. So we define the AXI Stall Monitor, which is a very simple module that you put between the hardware module and the interconnect. And this guy is configured with the stall that you find using the worst case analysis, and it takes back the control of the bus whenever it finds that a stall is endangers the schedulability of the system. And after taking back the control, it leaves the control again to the other hardware module in the system. This is just how it works, but I don't go into details now. This solution, unfortunately, has limitations. It's a solution that is great for real-time systems, but you need to know the bus workload generated. It's something that you can do in real-time systems, but not in mixed critical, for instance, the system that we've seen before with the HID9 accelerator and the critical accelerator, which is a mixed critical application. So we develop a more versatile and elegant solution that is based on smart buffering, basically. We got a paper currently under preview on that. Stay tuned, check it out, because I think it's very nice. Okay, besides the two problems that I saw that I was introducing before, also another thing that we were focusing a lot is on the criticality of the access control system, because the access control system defines critical functionalities that gives you the access to the peripheral, so it defines which controllers can access which peripheral. Unfortunately, there are challenges here because the access control system deployed in commercial platforms are quite limited, we've seen. And we would like to give minimum access to the controllers, basically to the peripherals, but we couldn't do anything fancy. Say. And those access control systems are sadly known to be common source of weaknesses. And this is the top 12 CWEs for 2021 from MITRE Consortium, the common weakness enumeration for hardware. And basically out of 12, 5 are related to access control system. So what we did is proposing a framework that's called ACER. ACER, in the Egyptian methodology, is the god of the underworld that basically check who is going in and out inside of the underworld, basically. So for building safe and secure access control system. And we build this on two pillars. We provide a module, as we did before, for access control system. But also what we did is providing security verification, a strong security verification. That is something that we really focused on, and we think that is a great way to provide security inside of a system. Concluding, well, what I would do if I had to integrate a system using third-party models or using complex models? Well, first of all, the first thing I would like to do is perform an extensive security and safety verification of the bus interactions. Many times the security verification is just focused on some very security-related problems, like I don't want that a key goes outside from my model or something like this. But also the bus interaction we've shown here that are important whenever you integrate a system at the system level. And we propose a paper also on that. It's going to be presented at DAC in a couple of weeks at the workshop at DAC. So check it out if you're interested in this thing. And we use the Tortuga Logic tools that implements this innovative information flow tracking to verify the bus interaction. I would like to thank them because they gave us very great support on that. Besides the verification, we provided some solutions. So maybe you don't trust your verification, maybe you don't trust your models, maybe you would like to have another level of security or safety with respect to just the verification. So what we did is proposing that. But these guys here, you have to integrate them in the system. It can be a pain, right, integrating all of them. So we defined our own interconnect. I actually coded my own interconnect that we call the AXI Hyperconnect, that basically integrates all of the solution that I proposed you before. And the AXI Hyperconnect itself is a research interconnect that is still under development. We still work on that. And it's able to enforce secure and safe bus interaction and also predictable from the point of view of the timing. You can use it standalone, or you can integrate it, what is more interesting, with an OS, an operative system, or an hypervisor. That's what we did. We integrated with Claire, which is an hypervisor for cyber-physical systems for the platform also that we are considering. And basically, in this case, when you integrate with an hypervisor, the hyperconnect itself is just an extension of the hypervisor for the models, for the controllers, and it provides functionalities to manage the controllers. These are just the features on the hyperconnect, and at the end, the same scenario I showed you before, and the mixed critical scenario, we integrate everything as before with the guy that introduced also the faults, but we put the hyperconnect in here to connect in place of the standard interconnect to connect to the memory. And we pass from something like this, so where whenever there were faults injected, the execution was broken, to keeping the system operational. And we got a slight impact on the performance that is because of the solution that solves the stalls, but still we can keep the system operational even whenever there are fault injected in the bus access. This is just to give an appreciation to all of the people that collaborated with me at UC San Diego, Tortuga Logic, the Retis Lab, and Accelera. I have got the great privilege of collaborating with all of them, and I would like to thank all of them, plus all of the industrial collaborators that gave us great feedbacks on all of our projects, Intel, Tortuga, and Leidos. I conclude with my contacts and references for the papers that we publish on all of this. All of this work is published, so you can check it out. There are all of the references. If you are interested in any of this, please let me know. Drop me an email, connect with me on LinkedIn. We can talk about if you want to collaborate. We're very prone for collaboration. I would like to thank all of you and the organization for inviting me here for this talk. It has been a very, very exciting experience. Thank you all.
Have any questions? Francesco? Anyone? We still have 4 minutes, so yeah, you can ask things. Okay.
Oh, I was fast then.
Yep. Yeah, I guess I just have 2 questions actually. So the first, it wasn't clear if you're trying to manage stalls by creating another route, dropping them. Like, how is this being handled?
How it's been handled by our solution, you mean?
Yeah.
So our solution, basically, the standard says that whenever you initiate a transaction, you cannot abort it. Right. So basically, you have to complete the transaction. So what we do is like completing the transaction, keeping back the bus, completing the transaction with fake data, basically. just to keep back the bus. After completed, we can get back the bus to the other guys in the system.
Okay. Yeah, it's a good workaround. And I guess the other part you talked a bit about, is this realistic?
Okay, yeah, sure.
In a lot of the hardware designs, you would expect there wouldn't be cases where it's going to request the bus and then wait. Under fault injection and other attacks, maybe that's going to happen. But if you assume no physical access, if something is maybe firmware or software driven and someone can...
So basically it's an issue if you use FPGAs because FPGAs are very easy to reconfigure. So you can put inside custom accelerators or change the functionality of the accelerators even on the fly if you wish. So that's a big issue for FPGA SoCs. Also in SoCs itself, it depends. It's not, I mean, on software, there are dependencies that depend. For instance, in the CDMA you've seen before, you got a method over there that if you are able to access, set up a request from a source buffer that is not going to respond to you somehow because there is a misconfigured peripheral or something like this. And while you ask for that read, you also submit a write. That is what the CDMA is doing. At that point, you're never receiving the read data, so you're never writing the data. So you are actually... Like, you can do it also via software. It depends like on how the platform is implemented, but it's an open door for injecting vulnerabilities. Yeah.
Yeah, that makes sense actually when you put it this way. With partial reconfiguration of an FPGA.
Also, yeah.
I would assume then all bets are off, but it also depends what part is an FPGA.
I mean, it's just partial reconfiguration. It's dynamic. Also, partial reconfiguration is just one of the methods that can happen. But it can happen also like whenever you got model that does speculative pass access. I mean, you can configure them with software and endanger the availability of the write. You don't expect that. At least I did not expect that before. So, yeah.
Thank you.
Thank you.
All right. Any last questions? Oops. Okay. Thank you, Francesco.
Thank you.